Next, we're going to move on to the multiple linear model. But now that we've done all this work to understand how vectors and matrices and vector spaces work, this is all going to go a lot more smoothly. So the multiple linear model, as we've said before, is designed to help us answer questions such as, is y related to x1, so response y covariate x1, after accounting for some other covariates x2, x3, so on. So we're going to use the same notation that we've used before, and let's just start with a simple example where we have 3 covariates. So the response is lowercase y, subscript 1 to n. The covariates are denoted xij. What that means is xij is the jth covariate for the ith subject. So for example, x21 is the second subject's first covariate. Now our model for lowercase yi is going to be the random variable uppercase yi, and it's the following. b0 plus b1 xi1 plus b2 xi2 plus b3 xi3 plus epsilon I. Now, whenever we write down a model equation, we have to specify what each of the terms means in the model. So let's start with epsilon I. The epsilon i's, meaning epsilon 1 up to epsilon n, are independent, normal random variables with mean 0 and variance sigma squared. The rest of the symbols here, we have b0, b1, b2, b3. These are just unknown numbers, parameters, and also sigma squared, which we just introduced in this normal distribution, is also an unknown number or a parameter. All right, so the first question you might have is, why do we keep saying this, that the multiple linear model is designed to help us answer questions such as effect of x1 after accounting for x2, x3, and so on? So we're just going to do a little example to explain why that's the right interpretation. So let's just look at 2 subjects, the first 2 subjects, subjects 1 and 2, and we're going to tell you what the values of the covariates are. So subject 2's first covariate is just equal to subject 1's first covariate plus u. So u is some number. Subject 2's second covariate is subject 1's first covariate plus v, and subject 2's third covariate is subject 1's third covariate plus w. So I'm just telling you that they differ by u, v, and w. Now, if we look at the difference in the expected value of the response for these 2 subjects, first thing to remember is if we do e y2 minus y1, because the expected value is a linear operator, this becomes expected value of y2 minus expected value of y1. This over here is just the linearity property for expected value. We're going to use this again in the next part. So just plugging in y2 here, I'm plugging in the right side of that equation. So that's exactly y2 according to our model equation. And we do minus y1, that's y1 from our model equation. And using this linearity property, what this means is if we have expected value of a non-random number a plus a non-random number b multiplied by a random variable, this becomes a plus b expected value random variable. So here we have a bunch of non-random stuff plus 1 times epsilon 2. So this becomes the non-random stuff plus expected value epsilon 2 minus this non-random stuff for the first subject plus expected value epsilon 1. Now the assumption is that the expected values of epsilon 1 and epsilon 2 are 0, so those go away. And we're left with this part minus this part. If we split that up into the contributions from each of the 3 covariates, we get this equation, so b1 times subject 2 first covariate minus subject 1 first covariate. Same thing for second covariate and third covariate. And we said that these differences were u, v, and w. That's just the labels we assign to those differences. So just to recap, we're looking at the difference in expected value for these two subjects. This is the difference in the expected value as a function of the three regression coefficients, B1, B2, and B3, and the differences in their covariates, U, V, and W. So the total effect is B1U plus B2V plus B3W. But the effect of changing just the first covariate is B1U. So one way to think of that is that if V and W were both 0, meaning the only difference between the first subject and the second subject was that their first covariate differed by U, then the effect on the response would be to change it by B1 times U. So that's saying if we controlled the values of the second and third covariate and only changed the first covariate, then B1 is going to be the effect of changing that covariate. So controlling for the other two, changing one, is the interpretation for B1. And that's why we say that these regression coefficients are the effect of changing one variable after accounting for or controlling for changes in the other covariates. Now here's where the matrix stuff is going to make our life easier. So the model for y1 to yn can be written all together in matrix form. So if we stack capital Y1 to capital Yn in a n by 1 vector, call that bold Y, and we put the covariates in their own matrix. So the first column here is going to be x1, 0, x2, 0, up to xn, 0. Now, I haven't defined what that xn, 0, the 0th covariate is, but I'm going to define it for you right now. These are just 1s. So this is just the one vector, the one column of 1s. And then what goes in the other columns are the other covariates. So the second column here is the first covariate for all the subjects. The third column is the second covariate for all the subjects. And the fourth column is the third covariate for all the subjects. Then that gets multiplied by the regression coefficients, B0, B1, B2, B3. And then to that we add the normal random variables, epsilon 1, epsilon 2, up to epsilon n. So what we get is y, which is an n by 1 vector, equals matrix X, which is an n by 4 matrix, matrix multiplied by vector B, which is a 4 by 1 vector, plus epsilon, which is an n by 1 matrix. So let's check all of the dimensions of these objects to make sure this all works out. So on the left side, we have an n by 1 vector. So whatever's on the right side also has to be an n by 1 vector. Let's look at xb. Can we multiply these together? The answer is yes, because x has 4 columns and b had 4 rows. The result is going to be an n by 1 vector or matrix. And we're adding to that an n by 1 matrix, epsilon. So we can add them together, and the result is an n by 1 vector, which matches what's on the left side. So at the very least, we haven't broken any of the rules for matrix multiplication. So again, I'm going to leave this to you as an exercise to verify that if you actually do the matrix multiplication, you get the regression equation given here, or the multiple linear model equation given here. So you can check that on your own. Okay, so that is a example with 3 covariates. In general, we're going to have some number p covariates, and we'll model yi as this sum over b0 plus bj times each of the p covariates plus epsilon I. And we can write these all together, again, in matrix form, but here x is going to have p plus 1 columns, because there's p covariates plus the intercept column. And the vector b is going to have, it's a p by 1 vector. Okay, now the statistical task here is we get to see data y, which is the vector lowercase y vector, which is the vector lowercase y1 up to lowercase yn. And we get to see the covariates x, that's data that's given to us. And we need to estimate all of the parameters in the model. So the parameters in the model are going to be the regression coefficients, but also the variance of the residual terms. The way we're going to estimate these parameters is by minimizing the sum of squared residuals. So what is this? Again, we're going to use the same notation where the residual sum of squares is a function of the some regression coefficient that you plug in, which I'm calling b star. So we're thinking this as a function. You give me a b star, I can calculate the residual sum of squares. And this is the formula, yi minus sum j equals 0 to p, bj star xij. All this is I'm taking what's on this part of the model equation, and I'm subtracting it from lowercase yi. That is the residual for regression coefficients b star. So again, think of this as it's a function of b star, and the way we get our estimates, the b hats that we like, is we minimize this function with respect to b star. Now, one way of doing the minimization is to take the derivative of the residual sum of squares with respect to each regression coefficient. So we're going to get a set of p plus 1 derivatives because there's p plus 1 regression coefficients. Here's what the derivative is with respect to the kth one. We get a 2, we pull that out, we get a minus here, and so you get a minus 2, and it's yi minus sum j equals 0 to p bj star xij, and the part that comes out of the inside is whatever's multiplied by bk star, which is xik. So we get a set of p plus 1 equations. To estimate the regression coefficients, we set all of the equations to 0. So here's the kth equation. So taking this derivative and setting it to 0, you get this equation. I've just moved the y's to the other side. And the estimate is the solution to this set of equations. So b hat j, xij, xik. Now, if we take all these p plus 1 equations and we write them all out, they look like this. And these are very special equations in statistics, and we call them the normal equations. So what I want you to do for an exercise, so it's not too hard to verify that this is the derivative. You can check that on your own. What's a little bit trickier is to verify that you can take the set of all of these equations, the normal equations, and write them in matrix form. And this is the matrix form. So the matrix is you take X, which we call the design matrix, transpose Y, the vector of responses, and that is equal to X transpose X times the regression coefficients. So that may or may not be obvious to you by looking at this equation, but what I want you to do as an exercise is to verify that this is the right matrix expression for these equations. The easiest way to do that is to start with the matrix equation and write out what they are, and then verify that they're the same as these equations. Okay. Now the goal here is going to be to get b hat. And we don't quite have it yet. What we need to do is to solve these equations to get b hat. The easiest way to do that is to multiply both sides on the left by X transpose X inverse. So X transpose X is going to be a P, so let's think about this. X is a N by P plus 1 matrix, which means X transpose is a P plus 1 by N matrix. So X transpose X is a P plus 1 by P plus 1 matrix. Now, if X itself has rank P plus 1, which we call full column rank, then it's true that X transpose X is non-singular, and therefore its inverse exists. and then we can do what we just described. You multiply on the left of both sides by x transpose x inverse, and that gives you b hat equals x transpose x inverse x transpose y. So I put this in a box down here. This is the formula for the regression equations. And I'll say that this is I'm not really going out on a limb here, that this is the most important equation in all of statistics. It gets used over and over and over again and in lots of different forms. Now let's talk about some other important objects here. I'm going to define y hat as x, so design matrix times estimated regression coefficients, x b hat. These I'm going to call the fitted values. And if we write this whole thing out in matrix form, we get the x, and then b hat is equal to x transpose x inverse times x transpose y. So you can think of this as it's a matrix x times x transpose x inverse times x transpose, that matrix times y. So let's call that matrix P. So all I'm saying is P is equal to x times x transpose x inverse times x transpose. This is how you get the fitted values. You multiply P times y. It turns out that P is a projection, and it's the projection that we care about. It's a projection of the data vector y onto the column space of the design matrix X. So let's see why that's true. So P, remember what we have to check to see that it's a projection is that it's symmetric and idempotent. So symmetric, let's do that one first. The rule for taking the transpose of a product of matrices is you take the transpose of each of them, but then you write them in reverse order. So P transpose is going to be x transpose transpose, which is x, times x transpose x inverse transpose. Now it turns out that x transpose x itself is a symmetric matrix. And one of the properties of symmetric non-singular matrices is that their inverse is also symmetric. So the transpose of x transpose x inverse is just x transpose x inverse. And then the last one is x transpose. And if you look at this equation, it's the same as this equation. So P equals P transpose, and therefore it's symmetric. Now, the next thing to do is to verify that it's idempotent, which you do P times P and verify that that equals P. This one's kind of fun. So P is x transpose x inverse x transpose, and then P again is x transpose x inverse times x transpose. So if we stare at this equation, something interesting happens. If we look at this part of the equation, x transpose x inverse times x transpose x, well, it's the inverse of a matrix times the matrix, and therefore that's just the definition of an inverse. It gives you the identity matrix. So this becomes x times I times x times I times x transpose x inverse times x transpose. So x times I is just x, and so we get x transpose x inverse, x transpose, which is P. So therefore it's idempotent. It's symmetric and idempotent, therefore it is a projection. Okay, so I said that it's a projection onto the columns of x. So why is that true? If we look at y hat, writing it out in this form, x times b hat, if we write this in block matrix form, we have the vector x0. What that means is in this case, it's just the one vector. The vector x1 is the value of all the covariates, the first covariate for the n subjects. So this is just another block matrix representation for x. So if we look at this equation, we do the multiplications. We get x0 times b hat, x0 times b hat 0 plus x1 times b hat 1, yada, 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 times xp times b hat p. So you get this equation, sum over j, xj, b hat j. Now, if you inspect this equation, this is just a linear combination of the covariates. So this has to be in the span of the vector, the columns of the design matrix, or the covariates, x0 up to xp. So it's a projection, and what is it a projection onto? It's a projection onto the columns of the design matrix X. All right, one more thing is, remember that if we have a projection matrix P, then I minus P is also a projection. So let's look at what that projection is in this case. So if we look at, I'm going to define what are called the residuals. The residual vector is just the responses, the observed responses minus their fitted values. We can write this as observed responses minus P times observed responses, because the fitted values are just P times Y. And then we can write this out as I minus P times Y. So the residuals are just the complement projection to the fitted values. If the fitted values are P times Y, then the residuals are just I minus P times Y. Okay, so this is I think an important way to think about what regression is doing. So Y is just the projection, Y hat is just the projection of the data Y onto the columns of X. And B hat are the coordinates of Y hat with respect to the columns of X. So we can think of the regression coefficients are just the coordinates of the fitted values with respect to the columns of X. So why do I say that? Because of this representation here, Y hat equals X B hat. So when we looked at linear transformations, we talked about the vector you start with as the coordinates with respect to some set of vectors X. So B hat, in this equation, you can see that B hat are just the coordinates of Y hat with respect to the columns of X. So this is like an alternative geometric way to think about what regression is doing. Normally we think about regression as we get the coefficients first, we get the B hats first, and then we figure out what the fitted values are. This is an alternative way of thinking about it, that first you do this projection of the data onto the columns of X and get the fitted values first, and then B hat just falls out as the coordinates of the fitted values with respect to the columns of X. And the last thing here, E hat, which I said before, is the projection of the data onto the space that's orthogonal, or the complement of the span of X. All right, so what we're going to be doing next is we want to know the sampling distribution of B hat. So what that means is we want to know what is the distribution of the random vector capital B hat, which is equal to B hat, except we're plugging in the model for the data instead of the data. So we can write big B hat, which is the random vector representing the distribution of the regression estimates, as X transpose X inverse X transpose uppercase vector Y. So just like before, we can think of this as we're doing some matrix times the vector Y. So I'm going to call that matrix M. So in order to figure out what is the distribution of this vector B hat, we're going to need to know something about the distribution of random vectors, meaning B hat and Y. And we're going to need to know if we know what the distribution of Y is, how to get the distribution of a matrix times Y, or a linear function of that vector. Okay, so let's start with the expected value of a vector. What do we mean by that? So just generically, I'm going to have the random vectors z1 up to the random variables z1 up to zn. I'm going to stack those into an n by 1 vector that I'm calling bold z. So it's a column vector. So what I mean by random vector, it's just a vector that contains random variables. That's it. First thing I need to define is, what does it mean when I take the expected value of a random vector? That's very simple. All it means is I take the expected value of each element of that random vector. So it's a vector that contains the expected value of each random variable in that vector. So that's very simple. Now, if I look at the expected value of m times z, this is just the expected value of another vector, namely a p by 1 vector, because m times z is a p by 1 vector where each element is a random variable. So let's look at this for a second here. The first element of that vector is going to be the sum j equals 1 to n m1j times zj. This is just the dot product of the first row of m with the vector z, and so on and so forth down to the pth entry. What I mean by this being each element being a random variable is that this is just a linear combination of random variables, and so it itself is a random variable. So if we take the expected value of mz, we just need to take the expected value of a bunch of random variables. Now, expected value of the first element, I'm just pulling it inside here. This is expected value of sum j equals 1 to n, m1j, zj, so on and so forth. Now, remember, we're going to be using this over and over again, that expected value is a linear operator, which means if we have a bunch of coefficients, mij, multiplying random variables, we can write the expected value of that linear combination as the linear combination of the expected values. So this first element becomes sum j equals 1 to n m1j expected value zj. Now, if you think about what this has become, this is really just the vector m times expected value of z. This is a typo. There should be no j here. So this is just m times expected value of z. The way you verify that is you start with this equation here and check that you get this vector here. And this all follows just very naturally from the linearity property of expectation. And look at that. Due to the magic of technology, I've fixed the typo there. All right. The next thing we want to think about is what do we mean? So we have expected values and we have variances. What does it mean to talk about the variance of a vector? Well, one way of thinking about it is we look at the variance of each element of that vector and also the covariance between every pair of elements of the vector. So we can talk about the covariance matrix for z, which I'm denoting as cov z. This is going to be an n by n matrix. The reason for that is there are n entries of z, and so there are n squared combinations of the entries. So we could do z1 with itself, z1 with z2, and we could do z2 with z1, z2 with itself, and so on and so forth. So we can represent the set of all the covariances for every element of vector as an n by n matrix, where the ij entry is the covariance between zi and zj. Now this vector is going to have certain properties. First of all, it's a square. This matrix is going to have certain properties. It's a square matrix, n by n matrix. It's also going to be a symmetric matrix. The reason for that is if we look at, for example, covariance of z2 and z1, we know that the covariance or correlation is symmetric in the arguments to that. So covariance of z2 and z1 is equal to covariance z1, z2. So it's symmetric because covariance zi, zj equals covariance zj, zi. That makes it symmetric. Another thing to note about these matrices is that along the diagonal, you have the covariance of a random variable with itself. This is equal to the variance of that random variable. And so I'm calling this a covariance matrix. Sometimes people will refer to this as a variance covariance matrix, but I'll just call it a covariance matrix. Okay. Now, so this is the definition of what we mean by a covariance matrix. We can also write a covariance matrix as an expectation. So let's see how that works. If we write covariance of z, it equals the expected value of this vector, z minus the vector expected value of z, so that's an n by 1 vector, multiplied by the transpose of that, which is a 1 by n row vector. So this is going to be a n by n matrix, a random matrix because it contains random variables. And what's going to show up is the ij entry of this is zi minus expected value of zi times zj minus expected value of zj, and then you take the expected value of that. That is just the definition of a covariance. And let's think about a entry on the diagonal. What do you get? What you're going to get is expected value of zi minus expected value of zi squared. That's just the definition of a variance. A variance is equal to the expected value of a random variable minus its expected value, whole thing squared. Okay, so we have that we can have this representation of the covariance as an expected value of a random matrix. What we mean by expected value of a random matrix is we just take the expected value of each entry of that matrix. Okay, now that's just what we mean by a covariance matrix. We're also going to need to know what is the covariance matrix for a matrix times a random vector. So just like before we did expected value of m times z, here let's do covariance of m times z. Now this makes sense because m times z is a p by 1 random vector, just like before. And so the covariance matrix for m times z is going to be a p by p matrix. All right, now let's push this through this equation here and see what we get. So this is the formula for the covariance matrix of mz. It's mz minus expected value of mz, which we saw before is m times expected value of z. And then this is just the same thing transpose. Now, if you look at this, we can pull out an m here. So let's pull out the m, and then we get m times the quantity z minus expected value of z. And the same thing over here, except we're taking the transpose again. If we write this out, this is the same. If we take the transpose of this, remember for transpose you put them in reverse order and you take the transpose. So you do this one transpose, which is this, and then m transpose. Now we have m times z minus ez times z minus ez transpose times m transpose. Since these are non-random, the m matrix, these are a matrix of non-random coefficients, we can pull them out of the expected value. And the way this works for matrices is similar to how it works for vectors. If you have one on the left, you pull it out to the left, and if you have one to the right, you pull it out on the right. So you get m times expected value of this stuff in the middle times m transpose. Now if you inspect what's in the middle, this is just the covariance matrix for z. This is the same exact equation. And so what we get is the covariance of mz is m times covariance of z times m transpose. Okay, so this is one of the important equations that you're going to have to remember. First one is expected value of mz is m expected value of z. And the second one, important property, is that the covariance of m times z is m covariance of z times m transpose. Next up, we're going to talk about the multivariate normal distribution, and we're going to use some of this, these facts we just derived about the mean and the covariance matrix for a random vector. So, a multivariate normal distribution is the following. So z, the vector z, n by 1 vector, has a multivariate normal distribution. This is the notation that we use. So z, n by 1 vector, tilde, n, mu, sigma, where mu is the expected value of the vector z, and sigma is the covariance matrix for z. So If z has a multivariate normal distribution, we write it like this, n mu sigma. And this is the density function for the joint density function for the random variable z. Has the following formula: 1 over 2 pi to the n over 2 power. N is the length of z, or the dimension of z. We take the determinant of the covariance matrix raised to the minus 1/2 power. And then we do e to the following scalar. So this scalar is written as minus 1/2 z minus its mean transpose times sigma inverse times z minus mu. So this is going to be a scalar because this is a 1 by n vector, this is an n by n matrix, and this is an n by 1 vector. So again, it's determinant of sigma to the minus 1/2, and then e to this scalar. This is a product of matrices that we call a quadratic form. We'll say more about quadratic forms later on. Now, we haven't talked about determinants yet, but determinant, you've probably seen the formula for determinant of a 2 by 2 matrix. A determinant is just a property of a matrix, and it's a scalar. So we'll show you some examples of how to compute determinants for simple matrices, but just for now, take it as determinant is just a number associated with a matrix. All right, so let's look at an example to make this a little bit more concrete. We're going to take vector z, random vector z, and we're going to say its expected value is the vector mu. And for this one, we're just going to say it's scalar mu all the way down. So each entry of vector z has expected value mu. And then we're going to say that the covariance matrix for z has sigma squared on the diagonals. So what that means is that the variance of each element of z, so variance of zi equals sigma squared. And then the covariance between zi and zj is 0 if I is not equal to j. So this matrix we can write as sigma squared, so pull that scalar out, multiplied by the identity matrix. And then let's just take this formula for the density at the top here, and we're going to plug in this stuff. So here's the formula. Density for z is 1 over 2 pi to the n over 2, determinant sigma squared I to the minus 1/2. And then e to this stuff, and we're plugging in sigma squared I inverse here. All right, so the first thing is that the determinant of a scalar times a matrix has a simplified form. It's going to be the scalar to the nth power multiplied by the determinant of the matrix. And I'll just give you the fact here that the determinant of the identity matrix is 1. So in general, so this is going to be sigma squared to the minus n over 2. Now in general, the determinant of a diagonal matrix is just the product of the diagonal diagonal entries. And you can see that from here. If you just take the product of these n diagonal entries, you're going to get sigma squared to the n, which is what you get here. And then you raise the whole thing to the minus 1/2 power. Now, if we look at this expression here, we have the inverse of sigma squared times I. Now, it turns out that that is just 1 over sigma squared times I. Now, remember, so I'm just telling you what the inverse is, but if you were to verify this, what you would do is you would take this matrix, 1 over sigma squared I, and multiply it by sigma squared I and verify that you get the identity matrix. So that's a pretty simple one you could do on your own. All right, so this is the second line here is a simplified expression. So just writing things out, we get 1 over 2 pi to the n over 2, sigma to the minus n over 2, which is 1 over sigma to the n over 2. And then since we have sigma squared I here, we pull out the 1 over sigma squared, so we get 1 over 2 sigma squared. And then I times z minus mu is just z minus mu. So we get minus 1 over 2 sigma squared, z minus mu transpose z minus mu. So here, this step would just pull the sigma inside here. So it's 2 pi sigma to the n over 2. Here, we're taking the transpose of a vector and multiplying it by itself. This is just the length of the vector, which we can write as sum I equals 1 to n zi minus mu I. This is just the definition of this inner product. And then if we use the fact that if you do e to the sum of a bunch of things, that's equal to the product of e to the individual elements. So this thing is raised to the n over 2 power, so we can write it as the product of this thing n times multiplied by e to the individual elements of this sum, which is e to the minus zi minus mu I squared over 2 sigma squared. By the way, if you've forgotten, this is the notation for taking the product of a bunch of things. You do I equals 1 with the giant pi sign to the n, and this means you take each of these things for each I and you multiply them together. It's the analog of the sum notation for adding a bunch of things up. So if you stare at this expression inside the product, this should look familiar to you as the density for a univariate normal with mean mu I and variance sigma squared. And what do we say when we're looking at the product of a bunch of univariate normal densities? That means that it's the joint density for a set of independent random variables with each of those densities. So we can write this as the joint density for a normal with mean mu I and variance sigma squared. And therefore, this sequence of random variables z1 to zn are all independent with mean mu variance sigma squared. Here we're using the fact that we assume that mu I was equal to mu for every I. All right, now we're going to work out some properties of the multivariate normal distribution. And these are properties that we're going to use over and over in this course. So it's really important that you get these properties down. Okay, the first one is that the multivariate normal distribution is completely determined by the mean vector and the covariance matrix. So let's go back and I'll show you what I mean by that statement. If you look at the joint density function, the only parameters that appear in the joint density function are this covariance matrix sigma and this mean vector mu. There's some other stuff in there like 2 pi, but that's just a constant. And n is just the dimension of the vector. So since the distribution is determined by the density, that if I told you that a vector has a multivariate normal distribution, the only 2 additional pieces of information you would need to characterize its distribution would be the mean vector mu and the covariance matrix sigma. So to recap, what I mean by that is if I tell you it's multivariate normal and I tell you the mean vector and the covariance matrix, that's all you need to know about the vector to completely know what its distribution is. Okay, so the next piece of information is that if I start with a multivariate normal vector z, and I tell you that its mean vector is mu and its covariance matrix is sigma, then I take this linear transformation of z. So I take the p by 1 vector A and the p by n matrix M, and I do A plus M times z. Then this vector, which is a p by 1 vector, has a multivariate normal distribution. So what I mean by this is if I start with a multivariate normal vector z, and I take a linear transformation of that vector and add a non-random vector to it, the resulting vector is going to have a multivariate normal distribution. And then by the first property, all I need to figure out is what is the mean of this transformed vector and what is its covariance matrix. And for that, we can just use what we learned a couple of slides back. So the mean vector of A plus mz is going to be A plus m times the mean of z, which is mu. And the covariance matrix for A plus MZ is going to be M times sigma times M transpose, where sigma was the covariance matrix for the original vector Z. So if you like, you can, as an exercise, verify that A plus MZ has a multivariate normal distribution with mean A plus M mu and covariance M sigma M transpose by using the transformation of variables formula for joint distributions or joint densities. All right, now we're going to use these two properties to derive the distribution of the sample average of a bunch of independent normals. So if we start with a vector y, a random vector y, that has mean b0 times the one vector. All this means is the mean vector is b0, 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 n times, and covariance matrix sigma squared I. We derived before that if you have a multivariate normal vector with this form, it's really the same thing as a set of independent normals with each with mean b0 and variance sigma squared. So what we're going to do is we're going to take the sample average of these things, but we're going to do it by taking a matrix vector multiplication with y. So I'll leave it for you to verify that if I do 1 over n times the one vector transpose, matrix vector multiplication with y, you get the sample average. That should be pretty easy to see, but you can verify that yourself. I'm going to call the resulting object y with the bar on the top, so y bar. This, we can think of this as a 1 by 1 vector. And if you look at this, this is just a matrix vector multiplication with y, and therefore it follows the rules for this kind of transformation of a multivariate normal. Here a would be 0 in this formula, and m is equal to 1 over n times 1 transpose. So by this second property, this thing has a multivariate normal distribution, and therefore to figure out what its distribution is, we just need to apply, you figure out what the mean of this is and its covariance matrix is. So the mean vector is going to be really a scalar, and the covariance matrix is really going to be a 1 by 1 matrix giving the variance of this scalar random variable. Okay, so let's do the expected value first. So this is E of 1 over n 1 transpose y. We know that this is 1 over n 1 transpose expected value of y. And so if we plug in expected value of y, which is b times the 1 vector, we're going to get 1 over n 1 transpose b times the 1 vector. If we pull the b out, since it's a scalar, we get b0 over n times 1 transpose 1. And we know that 1 transpose 1 is the dot product of 1 with itself. So you're just adding up 1 times 1 n times. So you get n. So you get b0 over n times n, which is b0. Okay, so we figured out that the expected value of this scalar is b0. And now we should do the covariance matrix. So the covariance matrix for y bar is you do m times the covariance matrix for y times m transpose. So you get 1 over n times 1 transpose times sigma squared I times 1 over n times the 1 vector. We'll pull the scalars out, so this becomes sigma squared over n on the left side. Pull the 1 over n out as well, so it becomes sigma squared over n squared. And then we're left with 1 transpose I1. And this just becomes 1 transpose 1 because I1 is 1. So we get this expression here. And again, 1 transpose 1 is just the scalar n. So we get sigma squared over n squared times n, which is sigma squared over n. So we've just used these formulas to verify that the sample average of a bunch of normals is normal, and its expected value is B0, and its variance is sigma squared over n. So we just derived the familiar formula for the mean and variance of a sample average using these multivariate normal matrix transformation formulas. All right, so these formulas are going to be really powerful, and it's going to make our life really easy to work out properties of the linear regression estimates, namely the sampling distribution of b hat. Okay, so let's go back to our multiple linear model formula. It's y equals xb plus epsilon, where epsilon is a vector of epsilon 1 to epsilon n, where these are independent normals. So that means that epsilon as a vector is multivariate normal with mean vector of zeros and covariance matrix of sigma squared I. Now, this means that the y vector is also multivariate normal. Why is that true? Well, that's just this property of the multivariate normal. If we start with a multivariate normal epsilon and we do a vector x beta plus a matrix multiplied by epsilon, the result is multivariate normal. So here the vector is xb, and the matrix we're multiplying it by, we can just think of that as the identity matrix times epsilon. So that means that y has to be multivariate normal. And to figure out the rest of its distribution, we just have to calculate the expected value and the covariance matrix. So the expected value, according to this formula up here, is going to be a plus m mu. We said that a was xb and m was I. Mu is 0, so it's xb plus I times 0, which is just xb. And then the covariance matrix for y is going to be I times the covariance matrix for epsilon, which is sigma squared I, times I. So you just get sigma squared I. So that means that y as a vector is multivariate normal, mean vector xb, and covariance matrix sigma squared I. All right, so now this is going to be really easy. We want to work out the sampling distribution for b hat, which is our estimator for the regression coefficients. Remember, the formula for b hat is x transpose x inverse times x transpose y. So we can think of that as this is a matrix, x transpose x inverse times x transpose, multiplied by the vector y. Therefore, b has to have a multivariate normal distribution, and we just need to work out its mean vector and its covariance matrix. So its mean vector is going to be that matrix multiplied by the mean vector for y, which is xb. So you get this expression for the expected value of b. If we move this bracket over one spot, we're going to get x transpose x inverse times x transpose x. Well, this is really easy. It's just the inverse of a matrix times itself. So this is the identity matrix, this product. So it's IB, which equals B. So we just shown that the expected value of B hat is equal to the thing it's trying to estimate, B. So that means that B hat is an unbiased estimator for the set of regression coefficients. Covariance matrix is going to be a few more expressions, but it's still pretty easy. So it's going to be m times sigma times m transpose. M is x transpose x inverse times x transpose. Sigma, the covariance matrix for y, is just sigma squared I. And then m transpose, we do transpose of each in reverse order. So it's going to be x transpose transpose, which is just x, and x transpose x inverse transpose. And we said before that this is a symmetric matrix, so its transpose is just itself. So we get x times x transpose x inverse. Now, let's pull the scalar out, and let's just multiply I by x, which is just x. So we're left with sigma squared times x transpose x inverse times x transpose x times x transpose x inverse, which is this expression here. And again, we have the inverse of a matrix times itself. So this thing just collapses to be I. So we get sigma squared times I times x transpose x inverse, which is just sigma squared times x transpose x inverse. So that tells us what the covariance matrix for the regression coefficient estimator is. It's just sigma squared times x transpose x inverse. And then finally, we can say the whole thing, since we know it's multivariate normal, we know it's mean and covariance matrix, we can say the whole thing is multivariate normal mean vector B covariance matrix sigma squared times x transpose x inverse. And that's the sampling distribution for the estimator of the regression coefficients. And it's very easy to derive now that we've done all this work to figure out properties of linear transformations of multivariate normal vectors. All right, one more property I'd like to show you is the covariance between the fitted values and the residuals when we view these as random variables. Okay, so the formula for the fitted values is the projection matrix times the responses. Remember, the fitted values are just the projection of the responses onto the column space of X. And the residuals are just the responses minus the fitted values. So you can write this as I minus P times Y, because you get Y minus PY. We know that Y, since it's a transformation of a normal, just P times the responses, its expected value is going to be XB. We get that, I'm not showing that here, but we get that by doing P times expected value of Y, which is XB. If you work out that, you're going to get XB back. And the covariance matrix is going to be sigma squared times P. So again, you get that by doing P times covariance matrix of Y times P transpose, and you'll get this. Same thing here. If you do these operations, you're going to get the distribution of the residual vector is going to be mean 0 and have this covariance matrix. Now, what we're going to work out next in more detail is the covariance between the fitted value vector and the residual vector. So what I mean by the covariance between the fitted value vector and the residual vector is I'm taking it's going to be a matrix, and the ij entry of the matrix is going to be the covariance between the ith fitted value and the jth residual value. So we can write that as an expectation of y hat minus its mean times matrix multiplication times e hat minus its mean transpose. Now the mean of e hat is 0, so this just becomes y hat minus xb times e hat transpose. If we write this out, we can get this expression. And this we can simplify to this expression here. So going from either here to here or here to here, this is quite a big algebraic step. So I'm skipping a few things here. What you can do is you can verify that if you take this thing and you multiply everything out, you're going to get this thing back, and use the fact that P has this formula. So take it by faith that this thing equals this thing here. Now, if you look at this expression, it's P, which is a non-random matrix, times y minus xb, which is random, y minus xb transpose, which is random, times non-random matrix I minus P. So we can pull the non-random stuff out on the left and on the right, and you get P times expected value of this times I minus P. If you stare at what's inside the expected value, this is just the formula for the covariance matrix for y. So it's y minus its mean multiplied by y minus its mean transpose, and then take expected value of that. So this is just the covariance matrix for y, and that's sigma squared I. So it becomes P times sigma squared I times I minus P. Pulling the sigma squared out, you get Pi times I minus P. And then distributing that, you get pi minus p times p. That's p. P's idempotent, so you get p again here. And so this is sigma squared times p minus p, which is 0. So what that means is that the covariance between any element of the fitted value vector and any element of the residual vector is exactly 0. So the residuals are uncorrelated with the fitted values.